Hello.
Good morning.
Good morning, everyone.
Good morning.
Hello.
Hello.
Still, some people are joining, so we'll just give it a few seconds in order to have everyone here. It seems that one of the participants has a problem with connecting to audio. So I think we should start and see how that goes. Good morning, good afternoon, everyone, and it's really nice to see you again, especially the ones with their cameras on. And I was told that Vladislav is joining us for the first time today.
Присоединяется к нам первый раз.
Is that correct, Vlad?
No, I've been joining for this week all workshops, all days.
Okay, but you have your presentation about yourself and your country and your organization, right?
Yes, there was some technical problem last week, but today I have some quick presentation. Yeah.
So let's start by seeing your presentation, and then we'll go to the class about today, about the life cycle analysis of PV systems. Then after that, we will talk a little bit and get your feedback about everyone's feedback about the project. So Vlad, would you like to start your presentation?
Yes, but I can't share my screen.
Okay.
It's disabled.
I will. I cannot find it. Ora, do you know how to?
Vladislav, try again. You have permission to share. Vladislav?
Yes.
Okay.
So you see?
Yes.
Okay, so my name is Vladislav Maksatov. I'm from Kyiv, Ukraine, working in the Ministry of Energy as a renewable electricity expert. I have a master's degree in energy management. So I'm from Ukraine. Ukraine is located at Eastern Europe, with population of about 41 million inhabitants. Capital.
У нас население 41,5 миллионов. И здесь на этом слайде
Installed capacity of electricity and electricity mix. So in Ukraine, about 50% electricity produced from nuclear power, about 30% from coal power plants, 10% gas, and last year we achieved 12% from renewables, which 7% from solar and wind. Yeah, Ukraine has a huge potential in wind and solar, especially in our south regions, where we have a huge solar installation and wind near the sea. Yeah, and due to last 3 years, we had a huge increase of power capacity, of renewable capacity and generation. It was provided due to introduction of feed-in tariff model. So the installed capacity of renewables increased more than 4 times. Most of them is solar. About 7 gigawatts, 1.1 gigawatt of winds, and a little biomass and small hydro. Also, in Ukraine, there are increased intensive development of small-scale generations of prosumers. Now we have about 40 hundreds of prosumers.
Сейчас у нас 40 тысяч потребителей, которые установили источники солнечной энергии. Пожалуйста, вот посмотрите.
Ukraine have, if I'm not mistaken, the large solar power station in Europe, Pokrovska, and also successful example is Sevash wind power plants, and have some projects with a capacity of 80 megawatt. One project, but this development, this sharp development led to problems, financial and technical characters. If we speak about technical problems, now our system is very unflexible. Most of it is nuclear base load, and in some hours we have problems with integration of variable solar and wind in our mix. As you see the slide, our TSO has to curtail renewable electricity, and it has to be paid by curtailed electricity has to be paid by feed-in tariff. Also, this increase of renewable led to increase in financial problems because lack of money for paying for all of this electricity, and lead to create some debts from state to renewable producers. In Ukraine, in 2012, Ukraine had negotiations with investors with participation of energy community, and signed memorandum of understanding. The main conditions was voluntary reduction of green tariffs in exchange of ensuring financial stability and by the government. Now this memorandum is almost successfully adopted. The financial problems still exist, but the situation is improved. What next? We are planning to achieve target 25% renewable in 2013 electricity sector, and revise our energy strategy and develop a national plan. We plan to achieve it through the auctions. We create all of legislation for providing auctions through the electronic system, but due to the problems of financing, the auctions was terminated for a few years. I hope next year we launch it. We plan to provide these auctions under feed-in premium model because for the existing objects was developed under feed-in tariff, where producers sell electricity to the state-owned guaranteed buyer. But we plan to let existing producers leave the balancing group of guaranteed buyer and so sell electricity directly in the market and receive the premium. And all of the new objects under the auctions has to be built only on the feed-in premium model. In this case, we also plan to introduction of guarantees of origin systems to confirm the consumer that electricity was generated from the green electricity. Introduction of corporate PPAs, where RES producer sell the electricity directly to the consumers without any support. And for small-scale generation, we're planning to implement some net billing or net metering systems. Is under discussion now. A few words about district heating. We in 2019 reached 9% of renewables in district heating system. Most of them from biomass, and we plan to achieve 30% of biomass in 2013, mostly with using biomass, and planning to introduce some kind of biomass exchange. We inspired by example of Lietuva with a bulk pool biomass exchange. Transport sector develops, renewables in transport sector develops not only well, but we see it is a problem in other countries too, where there are only more than 3% of renewables in the transport sector, and we're planning to achieve 10 or 15 in 2030. It's under discussion, but the electric vehicles really increasing in development in Ukraine. For example, in Kyiv, we have a lot of charging stations, and I see the a lot of electric vehicles and hybrid cars. Other measures that we're planning at construction new maneuverable generation for avoiding these curtailments of renewables, development of energy storage system. The registration have been developed, and we expect to be adopted during till the end of this year. Actually, one of Ukrainian company Tech has already built 1 megawatt storage and now testing it, and other companies planning to build almost 500 megawatt of storage. We're planning to develop offshore wind and Black and Azov Sea, using developing biomethane market, hydrogen, and stimulation energy crops, mostly for district heating biomass. What we're expecting from the seminar is to get acquainted about renewable development mechanism of other countries, to get a recommendation on the integration of renewables, to share Ukraine achievement and problematic issues that we faced last years. I was watching the previous video presentation from other speakers, and we especially interested in net metering, net billing system. I heard it introduced in Moldova, Georgia. Yes, and this seminar provided by Israel institution, and we're very inspired to know that Israel held auctions for solar with batteries, were successful auctions, and the price was about 4.6 euros, and that is lower than market price in Ukraine. So maybe some experience in these topics. Thank you.
Thank you, Václav. So it's always interesting to see what other countries are doing. So now we we will move towards the topic of the today. I'll share my screen, and my question to everyone will be, who heard of the terms or actually used the terms life cycle analysis before in their work? I cannot see everyone, but if you have any feedback, any comment that you think you would like to share with us, then just unmute yourself and share it with us. Maybe by raising hands, or sending the thumbs up on the screen if you used the life cycle analysis before.
It means valorized cost of energy.
In a way, yes. Yes. Anyone else? Okay, so I think this will be interesting to you if you didn't hear of it before. This presentation is based on my study I did for the master's degree a few years ago. So maybe some of the numbers will be outdated, but what we are talking about here is the approach and how to actually design and do such a system to evaluate solar energy component or solar energy technology. If you remember in the first class, when we talked about the community development projects, we mentioned that we should use two parallel tracks. One is to evaluate the community themselves, and the other is to evaluate the technology. So this technique can be one of the ways to evaluate the technology that we are using. Of course, we know this by heart now. Solar energy is the source, almost the source of all energies on Earth. If we talk about wind, if we talk about biomass, if we talk about that, everything is caused by the sun or generated by the sun. The amount of energy we receive from the sun is way much higher than what we actually consume currently. And this shows that the great potential of, it's not even a doubt, it's not even a question that solar energy is the answer for our energy needs. If we talk about Israel, southern Israel, the Arava Valley, which is the valley extends between the Dead Sea and the Red Sea, has a very high sun intensity. It's around more than 2,000 kilowatt hour per square meter, which is, if we compare that to what used to be the leading country in solar energy 20 years ago, Germany, this is way much higher than actually what's in Germany, which also shows that it's a normal decision, or what should be done for Israel is to move towards solar energy. Also, we want to keep in mind that solar electric generation has the highest power density per unit area. What does that mean? It means if we have 1 square meter of land and we want to utilize different technologies for renewables, then the highest yield will be by using solar energy, regardless of the efficiency of the panels that we are using. We have a mean here that actually I don't know if it's still valid. But anyway, later in this presentation, I will also introduce some kind of a calculation that can be used in order to give a value for, what does it mean if we are using this piece of land for solar energy? How many CO2 emissions we are preventing by using that technology? So again, just a reminder for all of us how solar energy can be utilized. There are mainly 2 approaches: thermal and photovoltaic. I'm sure that most of you already know this, and not even know this fact, you did already work on that. The main difference is what component of the solar radiation we are using. In the thermal, we are using the heat or the infrared component together with the heat in the light spectrum, and also with the photovoltaic, we are mainly using the semiconductor technology that stimulates generation of electrical current by exposing the material to the sunlight. Also, why we use solar energy? Lots of obvious reasons, but there is almost no pollution or no environmental impact at the point of using that energy. Of course, that doesn't account for the manufacturing process and where the material are coming from, the mining of the material. It is very flexible installation, so we don't have to stick to a certain type of installation. Like, it can be whatever the surface that we have. We can always have solar energy there, or solar panels that can generate electricity or energy based on the variables. So it can, we can utilize the maximum or part of that maximum of outcome of that energy. It can be easily integrated in different services. If we talk about buildings or open spaces, or even common spaces like parks or sidewalks, or that, it's very easy to do it. It's much less complicated than any of the other options, especially if we talk about stationary flat plates that don't require any tracking. So there are no moving parts, no mechanical parts, which means much less maintenance and service required. Also, it's very easy to scale it up. Once we install the system, that doesn't mean we are stuck with the size of the system. It can be easily adding other modules, expanding the inverters, adding other inverters, all that. Why, if we talk about, for example, a wind farm or a wind turbine, once we have the turbine, then that's it. We are stuck with the size of the turbine installed, or of the installed capacity. A general look on what technologies are available for solar energy, for mainly photovoltaics here. So we have silicon-based, and that's the most common. The most common, I think, now are multi and single crystalline. I don't know if the ribbon cast is still in use of the silicon technology. Amorphous silicon still exists, mainly because the amorphous silicon is flexible. You can use that as a cladding material for rooftops. It can be shaped in different forms to meet the the requirement of the surface that we are using. There are other technologies that are not silicon-based, and there is always competition between different research groups looking into alternatives for silicon. So we used to have the CIS technology that I don't think it exists anymore. I think it died something like 5 years ago. Actually, an outcome of this study was that the CIS technology is too expensive to be used. The balance of energy is not good. We are investing more energy in building the technology than what we're getting out of it in its lifetime. So it's not feasible. The cadmium telluride, the CDTE, I think it's still in use, but in much less. The dominant now, as I said, is the silicon-based, mainly single and multi-silicon. There are also all these new concepts of what can be done. Solar concentrators have very high potential. There have been some trials in the past. I will talk about 2 of them here. There is the organic-based or mimicking the nature and how leaves in plants actually generate their energy. And the quantum cells that still needs a lot of development. One of the main examples for the concentrator, here we are talking about the solar concentrator systems, is the Sol Focus technology. Sol Focus was created by 2 students at Ben Gurion University in Sde campus in the south of Israel. And they actually moved ahead and established a company in South California that mainly manufacture this type of cells. It's a very smart design. If we look at how it works, actually it uses primary and secondary concentration of solar light with the use of solar geometry to concentrate that. I think they used to get something like 300 suns concentration for their system. So this unit, the one that we see here, is a 7 kilowatt array. Another system, let's talk one more sentence about this one. Unfortunately, the company didn't survive for a long time. They actually operated for something like 7 years. But then because of the mass production of flat plates and the difference in prices between flat plates and the Sol Focus system, Sol Focus simply died and couldn't compete with them. They didn't manage to get enough clients to buy the technology. Also adding in mind the complexity here, like because it's a concentrator system, one of the main requirements for concentration is to track the sun hourly and seasonally. So we have to have dual axis tracking. And that makes the system more complicated, more mechanical parts. Any disalignment with the sun will cause lots of losses. So people always prefer simplicity, especially if we get the same amount of output. And recently, the cell efficiency for flat plates is increasing, so it puts all these different options at risk. The other system of concentrators is what's called flatcon technology or flatcon systems. Very similar approach, but the main difference is they are using lenses instead of mirrors. So the concentration is done via using a lens that concentrates the sun on a small spot where the cell exists. You can see my pointer, right? The mouse. Over here, you see the bright side, that's where the cell is. And one of the main advantages of using concentrator solar systems is the reduction in using the cell material. 10 years ago, 12 years ago, silicon was very expensive, and that's why the alternative technology option was very active. And one of the main branches of how to overcome that cost is even one use less material, less silicon, and the other is to find alternatives for that. So using less silicon means we need to generate or we need to have higher solar radiation per square or per unit area in order to have a good output. The main challenge also here, together with Sol Focus, was the cooling, because here we get very high temperature, and here you see all these small pipes that some of them are actually the conductors in order to transfer or to evacuate the energy, and the other is for cooling the cell material. This is also another system that was built by this company. I think also Flatcon maybe still exists. I didn't hear anything about them for the last 3 years, but before that they were still out there. So that's by the technology type, and by installation type we have 3 different levels. What we can talk about is like centralized photovoltaic power plants, and that's we are all familiar with that, with large fields. We get thousands of square meters. We install the system, we connect it at high voltage grid, and we distribute the power. Or on the other end is the integrated building integrated photovoltaic, and that's like on the rooftop, on facades, and something in between, which is a combination of both. Like if we have here, call it urban integrated, but in the study itself, it's called the kibbutz integrated, because the field, the area of study was Kibbutz Ktura, where the Arava Institute is located. And the main idea is to utilize all the different potential areas for installing solar energy and see what is the outcome that we can generate out of there. Yeah, giving more examples and also the comparison of these different technologies by like why.
Этих разных вариантов мы смотрим, почему и чем хороши централизованные установки, городские установки и интегрированные в здание установки. В некоторых местах земля – это очень дорогостоящий товар, да, очень сложно получить землю, и люди стараются использовать все доступные поверхности. Тогда мы как раз говорим о преимуществах интеграции в здание. Но в централизованном случае мы максимизируем результат, да, мы используем разные, собственно, установки, разную высоту для того, чтобы снизить потери на затенение или от затенения. И когда размер не проблема, да, тогда, собственно, эффективность затрат это не вопросы, потому что здесь масштаб уже высок, и затраты на генерированный киловатт-час нормализуются. И, в общем, они становятся минимальными. Что касается городской интеграции или интеграции в кибуцы, вот здесь вот вы видите тротуары или использование таких конструкций, которые дают тень людям в парках. Также установки на крышах, в местах общего пользования, в зданиях общего пользования, если, например, мы говорим о кафе или столовой, о террасах, да, там тоже мы можем установить наши солнечные панели, которые будут отбрасывать тень. И здесь, собственно, пример крышных.
For my neighbors, it was like a very unique way of thinking about it. I have a nice terrace, and I wanted to put some shading material on or shading structure on the terrace. And everyone here, even that I live in a city that's very warm, still like now, I think today will be like 24 degrees outside. So rainfall happens only once or twice a year. But even with that, when people want to have any shading material or structure, they use that tilted roof, similar to what's in Europe, because it looks nice. But it's totally out of the architecture here. It doesn't fit with the nature of the city. So I wanted to, instead of using that, to use the solar photovoltaic system as the shading structure. And I was very surprised to see that actually nobody did it before. It makes lots of sense. You know, you have a space, you want to use it. And in this way, we have a dual usage of the space. We generate electricity. And also, I can sit there when it's noon time, especially that area is south facing. So it reduces the heat that the house is getting significantly by having this shading structure. Also, it's mainly common in the US that actually amorphous silicon is used as cladding material and to prevent insulating material as well, to prevent water leakage and all of that. They already use that. It's a form of plastic. So instead of using the plastic or the insulation rolls they have, they use the photovoltaic technology, and that's also doing the dual function as well. And because of the building integrated photovoltaic, the option of feed-in tariff became like very popular. Everyone can be an energy producer. Of course, we will not talk about the downside of that and how it's limiting or adding more variables to the grid and the grid stability. But here we are talking about how households can benefit from that and what's another incentive for them to be more, to a certain extent, independent energy-wise. And the main downside of this is that the responsibility of cleaning, maintaining, and making sure the system is working lies on the owner of the household itself. Also, the size is an issue. we are always limited by space, so that means the option of how much kilowatt hours we can generate is very minimum. And this one is very suitable, which I always say that we need first to look into energy conservation and saving before we talk about finding other sources of energy. Recently, or it used to be, and I think it's still valid, that the major consumer of energy in buildings is the heating and the cooling. So first, we need to look into our energy efficiency in the building, thermally, and how the building is working, is functioning. Try to maximize that efficiency, and then we see how much of that required energy we can rely on solar instead. So let's get to the topic. The life cycle or energy life cycle, it's mainly looking into the both the inputs and the outputs of an energy system. The inputs or the input energy, mainly called as embodied energy, how much energy we actually invested in order to build this system, this technology, and that can be a measure for any technology that we are using or anything that we are manufacturing. And the output is what is the potential output energy in the lifetime of that technology that we can generate, or what's the energy, mainly what is the energy balance of this energy system. To compare the two of things, and or to be able for an energy source to be competitive with fossil fuels, we have to have two important characterizations. One is that the energy supplied by the system over its operational lifetime should be significantly greater than the input energy or the embodied energy, or simply that we didn't have a losing investment. We didn't put more energy in something that will generate less energy than what we invested in building it. And the other is the net emissions, and this is mainly to be competitive with the fossil fuel. The net emissions of greenhouse gases from that system should be significantly lower than the alternative, which is what if we used fossil fuel source instead of this system. So this criteria will be our main judgment or our main evaluation for the technology that we are using. So how we measure that is mainly by looking to the life cycle energy analysis. So the life cycle analysis is looking into the life cycle of any product, from manufacturing, even mining, even before that, all the way down till decommissioning and disposal. And we take every step of that process and try to account for what different resources that product required in order to be manufactured, used, delivered, assembled, and even disposed. If we talk about life cycle energy analysis, then we are only focusing on the energy component of that analysis. Then what we need to do is account for all the input energies that we used for building the module. If we talk about photovoltaic here, then we are talking about the module itself, the cells, the frame and the encapsulating material, the packaging, transformation, and also the balance of system, which is the support structure, the tracking if it exists, and cables and all the different non-photovoltaic components of our system. Then that will be compared to the savings, how much energy we are actually saving by using that technology afterwards. Like, in other words, what is the output of this technology that we are using? So as if you noticed last class, I love flowcharts. So this is a simple flowchart of how actually we do this comparison or this life cycle energy analysis. The first is like we prepare a list of the different technologies, photovoltaic technologies that we want to compare. And here I'm talking about photovoltaic. This can be used for any other technology. If we want to talk about the different technologies used for biomass or for geothermal, for tidal, all the different options that we can be listed. Then the first calculation needed is how much energy we are getting out of this technology. And for that, we need to get what is the initial bulk of energy available, how much solar radiation is there in that specific location that can be utilized to start with. We take also into consideration the heating potential of the PV. We know that the efficiency of a photovoltaic cell is dependent on mainly two things, I would say. One is the available solar radiation, and the other is the surface temperature of the cell itself, or the cell temperature. And then we need to understand in that specific location, what is the potential of heating that we will be dealing with. Then we talk about the efficiency, and this is mainly the nominal efficiency, how much the manufacturer are saying that this panel can convert the available solar radiation into energy. And we talk about the temperature, shading losses, and ground cover ratio. This is very important if we talk about large scale or centralized photovoltaic power plants. Ground cover ratio mainly means if we are using a tracking system for photovoltaic, then for sure we need more land than if we are using stationary, because the movement and the potential shading that can be introduced there. I will talk a little bit more about it later. Then after collecting all these variables, we start the calculation, which is calculating what is the cell temperature. And this is mainly modeling here. This is what we are talking about, is before you implement the system. It's like, what is the potential cell temperature that we'll be working on? And this should be hourly, like every hour, or even if every 15 minutes, what we are expecting the output will be. Then the same thing with the collectible energy, calculate how much actually solar radiation is falling on the surface of the panel based on the installation we are having. And then from that, getting the yearly output of the photovoltaic. Then on the other hand, we do the embodied energy, or the energy input in the system. And that's, first of all, we need to define our boundary of system. If you remember, we said that life cycle analysis means including everything from mining, from even, some people go far as when there was a brainstorming session about using or designing that technology, people sat in a room and they used a power source as light, for example, or heating and cooling that required energy. So, should we account for that or not in our calculation? If we are having workers going to the factory that builds that technology or manufacture that technology, how much should we, of the energy they are using, should we account for? The food that they are bringing with them, the light system used in the factory, what about their homes, the transportation that they are using in order to go back and forth. So this all we should define define our boundaries, what we account for and what we don't account for. Then we look into the different data available for the processes. We break down the manufacturing process of a photovoltaic cell, and then we look into each step and how much energy actually we require in each step. And after that, we do the calculation of the embodied energy, which is the sum of all the energies that was used in the different stages. Then after that, we calculate the different measures or the different factors, first of all, the life cycle energy, which is the total number, the energy payback time. And the energy payback time is a very interesting topic for engineering, or number for engineers, and for economists. It's similar to the return of investment. If we talk about investment, it's like in how many years, or what is the amount, the percentage of yield, output energy, compared to what we invested in building the system. So the energy payback time is a very useful measure. Then what we can do is also calculate, in order to get to these different numbers, calculate what is the demand of electricity in this specific location. Do we actually need, what is, if there is energy, extra energy, and what will be done with that extra energy? If we are using transmission lines, then for sure there are losses in that transmission line. We should all account for this in order to calculate our, to get an accurate numbers at the end. And what we also use is, in order to compare different installation types, we come up with different scenarios of what installation we need to have. For example, if we are using a centralized power plant, then we know for sure that the power will not be used in that centralized power plant. We need to transfer the power to somewhere else. Then that introduces other variables, like what we talk about, the energy losses in transmission, and energy losses in transformers, like to increase the voltage level in order to be able to be transmitted, then reduce it in order to be used, and all that. And based on that, we do our calculations on how much actual energy we have at the end of the wire, at the end of the cable. After that, we use the equations that we'll talk a little bit about them here, like calculating the life cycle energy and the CO2 offset. The CO2 offset is a very interesting parameter that mainly gives us a very good indication of, like, now currently everyone is talking about reducing CO2 emissions, but nobody is talking about actually how to do that. If they say using renewable energy for sure reduces your CO2 emissions, but if you have very limited or very strict goals to meet and very limited options of technology and available land, so how to decide which technology you need to use in order to have the higher CO2 offset of your system, electric system? So here we introduced a new parameter, which is based on the previous, all the calculations, that gives us a value for that piece of land. What is the potential CO2 emission savings if we are using this technology or another technology? So let's go more in depth and look into the input energy or the embodied energy in a photovoltaic cell. Here we broke the system into 4 components or 4 elements. The cell material itself, we talked about that, if it's silicon or other than silicon, multicrystalline, single crystalline. Then we talk about the capsulation material, and that's the thin film that actually they put on for protecting the degradation and holding, like to hold the cell itself, the conductors that they put on the cell in order to collect the energy produced. Then we talk about the balance of system, already mentioned that, the tracking system, the support structure, the frame of the panel itself, all that is included here. And then transportation. Once we have the panel ready, the inverters, all that, how we going to transport that from the factory to the place where it will be used. Then we talked about the system boundaries, and this in order for us to proceed to have an output, we need to have limitations. Otherwise, we can go forever in our calculations. So the best, one of the best standards to be used is the ISO 14040, which is also the terms of the International Federation of Institutions for Advanced Studies, which decide, like, you know, gives us these different levels of embodied energy. If we talk about level 1, and that's mainly the direct energy used in the process. In the factory itself, we are running a machine, how much energy that machine is using. And energy of transport for mainly the raw material for the system. If we talk about level 2, then what is the energy? We account for the energy used to get to the energy source that we are using, and the direct energy for getting the materials and energy for transportation, including the materials and other components. So if we go every level, the level 4 actually almost accounts for everything. What the standard says is that if we get to the second level of this scheme, we are already covering 90% of the direct energy input for our system. So this is very helpful. That makes our life way much easier when we do the calculations. If we look, just to give it a perspective, if we look to level 4, then we need to look into the energy acquisition of energy sources that used directly in manufacturing the machines. So we are going 3 levels in the machines that are actually being used to manufacture our system. So in this way, it's, you know, that can be a nightmare, especially now with globalization, and that every piece of that machine can be produced in a different country, and that every country has its own different energy system, which is mainly here we look into the mix of different energy resources in that country, if it's fossil fuel or renewables or hydro or you know, all the different nuclear as well. And then we look into the machines that the energy used for manufacturing the machines that were used to manufacture our machines. So that can take like several years only looking or collecting these numbers. So what we will stick to for today and in general is that 90% is good enough for us. And that's only level 2, which is accounting for the direct energy used in the factory and transport, energy for transport of material and of in the factory itself for workers, for export, and the direct energy used for mining the material itself. So let's look into what are the processes of manufacturing a silicon-based cell. So we have, let's start from the bottom. We have 2 different types. We have the cells as for the multicrystalline or single crystalline, or the crystalline silicon. And we have the amorphous silicon, which is mainly a thin film or a thin film deposition on the material. Ribbon is also similar to the thin film. It's something in between if you think about it. So anyway, we get the sand, the silica sand. We melt that at very high temperature. Then we get a certain type of silicon that actually is used. From that, we get to the cooling of the silicon, and then we have the 2 different approaches with one single crystal, and then we have the monocrystalline of the silicon where all the cells are aligned in the same direction, or we have multi crystals that forms the crystal of the ingot itself, and from there we get the 2 different types. Then sewing that ingot and getting the different cells. So there are losses also on all these processes when we get from the silicon all the way to the cell. Losses, I mean, other than energy losses, there are material losses over there. We also looked into other types of cells. We looked into the CDTE and CIS. And for that, there is a totally different process because they are using different materials. So here also we need to look into the different stages of manufacturing that. What I found out is like the process of manufacturing of these alternative technologies is much more simple than the process of manufacturing the silicon-based cells. So when we look into the different stages and we for that there are like available data sets that already provides the energy uses for different processes in manufacturing, and they have a very good number of information or of data actually on what can be what is the numbers, what are the values of energy used in order to go on each of these steps. So after we get all the energy inputs, we account for the different variables. I'm going a little bit faster because we want to give some time for discussion and also afterwards for the projects. So I'm touching mainly on the principles of the process. If you need more details and if you are interested in more the detailed calculations, I'm very happy to send you more material about that. It's simply my master's thesis, so I'm very happy to share it. We actually did a publication on that. So we look into the output energy of the panel, and for that we need to calculate based on, as I said, hourly, and even if we get higher resolution than every hour, then that's even better. We'll get more fine tuning for our system. And then for any photovoltaic cell, we have two main variables that we need to look into, or restraints, I would say. The collectible solar radiation, how much is there to start with, and what is our cell efficiency. It's like, okay, we have an X amount of energy to start with. Our cell can only utilize 16% of that. Then this is where actually we are starting. We are starting at 16% of what is available for us. And these are the main limitations of what we talk about. Everything else is variable. So in order to calculate the collectible energy, or what is out there, we use the solar radiation calculation, which is mainly looking into the three components of the solar radiation: the global radiation and the diffused radiation. And these are like what we can measure without having the direct sunlight. And for sure, the main component is the direct beam of the solar radiation. If we look here, this is a very good illustration of what we are collecting. Diffused and scattered, or the diffuse is caused by scattering of the solar radiation, mainly by particles in the air, by the atmosphere, by clouds, by buildings. There is the albedo, and that the reflected also accounts for both the global and the diffused, and the direct beam, which is the perpendicular to the surface that we are considering. And for each one of them, we have to account for the coefficients, the incident angle, and the coefficient for that specific type of radiation. These are also available if you want to get more in depth of how to make these calculations. It's there. We already have and that's in the last I would say 7 years, software that already is working. Like you just define where you are, and then the software actually does this calculation for you. But then it depends on what we don't like is like to depend on someone else defining their variables and limitations. What we want to do is to be in control of that. So we can, depends on how significant this is for us, we can build our own.
В зависимости от того, насколько это для нас важно и значимо, мы можем сами построить свою модель и все детали, все переменные туда внести, или использовать вот уже существующие, как я сказал, примеры программного обеспечения. Это первое, да, первое, что мы считаем, собираемая энергия, получаемая энергия. А что касается эффективности ячейки, здесь мы просто полагаемся на то, что публикуют производители о своих технологиях. Вот эти цифры немного устарели, повторюсь. Сейчас, мне кажется, по монокристаллическим кремниям некоторые технологии уже заявляют 24% номинальной эффективности. Но, опять же, это то, что мы, если строим свою собственную модель, и у нас эта эффективность переменная, то каждый раз мы вносим правильную цифру. Если же мы используем уже готовое программное обеспечение, то там есть база данных по всем производителям солнечных панелей, которые существуют, и по их показателям. Здесь что важно увидеть? Это различие между Sol Focus и FlatCon, между вот этими технологиями и другими оставшимися технологиями. И вот это как раз то, что я говорил о высокой концентрации и повышении результатов и повышении, собственно, объема энергии, который мы получаем на ту же самую единицу территории. Также важная цифра – это температурный коэффициент. Это то, сколько потерь мы получаем при повышении температуры ячейки. Если вы прочитаете характеристики любой панели на фотоэлементах, то вы увидите, что там есть такое STC. Это стандартные определенные условия. Это включает 25 градусов температуры ячейки, дальше масса воздуха 1000 киловатт, прошу прощения, 1000 ватт, 1 киловатт солнечного излучения. И все эти цифры, и, собственно, поэтому мы не используем цифры от производителя, потому что это функция переменных. Если мы меняем температуру, да, то тогда эффективность ячейки падает. И поэтому знак минус здесь означает как раз, что если мы повышаем температуру, мы снижаем эффективность ячейки. Если солнечное излучение повышается, тогда эффективность ячейки повышается. Если масса воздуха повышается, то есть у нас меньше прямого излучения и больше глобального и рассеянного излучения, да, если вот сюда вот вернемся, мы видим, что рассеянное и глобальное излучение, у них факторы больше, чем у прямого излучения.
So based on that, what we do is like we use a model that was generated by one of the researchers, a US researcher. Again, I don't remember his name, but I have that reference if you are interested, of how to actually calculate the cell temperature based on the atmospheric temperature and the temperature coefficients of that. And here we have mainly two variables, T1 and T2, and these both are dependent on the material of the module. What was used? Is it glass? Is it plastic? Is it 2 layers of glass, 1 layer of plastic, and 1 layer of glass, or all that? So the TM is the surface module temperature measured, and then or calculated here. Actually, it can be measured or calculated here. If we don't have it measured, then we can actually have a good estimation of how much it is. The TA is the ambient temperature. This is the measured temperature of the location where we are. The solar radiation or on the module, and the solar radiation as a reference, which is the standard test condition one. The wind speed, because of the to calculate or to account for the cooling effect of the wind on the panel itself. Then we have empirical constants based on what type of material is being used. And the delta T is another constant that will be used. And here I give a different, the reference values of these different coefficients that can be used over there. So by simply plugging in the ambient temperature and our solar radiation and the variables here, we get to the different, what is the potential cell temperature that we are getting. By knowing the cell temperature, we can go back to the nominal temperature coefficient and see how many degrees above 25 we are getting. And for each degree, we're having a 0.4, for example, 0.4% for the multicrystalline decline on our efficiency. Then to count for the ground cover ratio, we said that the ground cover ratio is how much of the land we can utilize, we can use for our system. And that there are different, if we want to get numbers that are already published by other researchers, we can do that, or we can work with geometry and try to find out what is shading that is acceptable, amount of shading that is acceptable for us, and what is not. So if we keep in mind, if we are, for example, using a polar mount, or not a polar mount, tilt equals latitude, where, for example, in Jordan and Israel, we use around something between 20 to 25 tilt angle for the panel in order to maximize the yield between winter and summer when the sun is angle is different in the sky. So we know if it's stationary, then any morning hours until a certain hour that can be calculated where it's actually defined as the sunrise hour for the PV panel. Before that, we know any energy there is losses. So we can allow a certain shading at that hour of time, because anyway, there is a minimum output of that system. We know that the maximum output is around solar noon, which if we talk about June without the daylight saving time, then it's exactly 12 o'clock midday. So around the solar noon, we want to have the maximum, we know that the maximum radiation is there. So we want to reduce as much as possible any potential shading to utilize the maximum output. So for that, what we assumed in our study is that 15% losses is allowable. We can have that. And for flat plates, and only 2.6% for concentrators. Why is that? Why for flat plate we are having 15%, but for concentrator we're having much less than that, mainly because of what is the investment that we are putting in this. Concentrators, we said that they are more expensive. They are dual system tracking. So the potential, and because they are more expensive, then we are talking here about mainly large scale and centralized power plants. So for centralized power plant, every kilowatt hour counts, and we want to have the minimum losses possible. For flat plates, the story is different. It's like we usually, what we assumed here is like we are usually using flat plates for dual function, for shading and for electricity generation, for to provide shelter and for electricity generation. So that's why 15% is kind of acceptable, and also 15% out of 2 kilowatt system is not as significant as 2.6% or 3% out of 1 megawatt, if we talk about value of that. And for this, the ground cover ratio for flat plates was 50%. So if we have a piece of land, 1,000 square meters, we are covering half of that with our solar panels in order, and this way we are reducing the amount of shading. In order to meet the 50%, we are allowing 50% losses. If we increase the the ground cover ratio, then we get
коэффициент покрытия земли, тогда мы получаем больше тени. То есть мы ставим больше панелей на той же территории, значит, расстояние между рядами меньше, и, значит, потенциал затенения друг от друга у них больше. То есть вот здесь вот 30 градусов и 0,5 коэффициент покрытия земли, да, здесь практически нет, вообще нет затенения от одной панели на другую. И здесь мы можем посчитать расстояние B в зависимости от угла наклона панелей, от размера панелей, и это позволяет нам как раз вот это посчитать и получить 50% коэффициента покрытия земли. Если мы говорим о слежении, о трекинге,
of shading will cause us much higher losses of that. So we are more strict with the tracking, but that gives us even lower ground cover ratio. Here we have between 12 to 17% of ground cover ratio for that. Is this clear? Okay, I see people shaking hands, so I'm assuming this is clear. Okay, so let's get into how to evaluate that. Now, after doing all these calculations of what we spoke about, we have the input energy, the energy that was used in order to manufacture our system, to transform the system or transport the system where we want to use it, to build the system, and also what is the outcome energy from that system based on the specific installation type. If it's a single axis tracking, north-south or east-west, or polar tracking, or fixed polar mounting, or even fixed with tilt equals latitude, all that the numbers we have. So we calculate the energy payback time, which is simply the ratio between the two energies, similar to the return of investment that we spoke about a little bit before. The problem with the EPBT is that it doesn't give you the sense of time. We have the energy generated as a unit, but the system is functioning like most of the PV panels. They come with a 20-year guarantee. The inverters come with a 10-year guarantee. So how do we account for that? So we calculate the energy return factor, which is how much energy we are actually getting out of that system in its lifetime, which is mainly the energy payback time multiplied by the lifetime of the the lifetime of the system divided by the energy payback time. For different installations, we used different ground cover ratio. We said here that the maximum we allow, or the minimum we allowed for stationary was 50%, and that's mainly because tilt equals latitude, which is mainly this setting, the last one in this graph. Tilt equals latitude with 0.5 or 50% ground cover ratio. Stationary with zero tilt, and that's mainly flat plate, putting it in the ground. That means 100% ground cover ratio. Of course, we cannot get 100% because we need access. We need to get into the panels to do service, to do cleaning, if there's any electric issue that needs to be solved. Single axis tracking, that can be north-south axis, meaning tracking the sun from sunrise to sunset, or east-west tracking, and that means tracking the sun in between winter and summer, because of the solar angle is different depending on the season. And for that, we get also 50% ground cover ratio. Polar tracking. Polar tracking is a very smart utilization of mathematics, because what we know is, like, if we put a single PV at tilt equals latitude. So if we are, for example, here in this region, we are at 28 degrees north. So if we tilt our PV at that amount, then that normalizes the energy between winter and summertime, the energy that we are getting on that surface. So what if we do the same thing, but we start rotating the panel east and west, so north-south axis? That meaning we will meet the sun when it's rising, and we stay with the sun until the sunset. So in this way, we increase the output, but also because the mutual shading has higher potential, then we have a lower ground cover ratio. At the extreme of the tracking is the dual axis tracking, like in the concentrator systems, where we have the smaller ground cover ratio. So to account for, now we want to move from energy calculations into what does that mean for us? What does it mean as CO2 emissions, greenhouse gases emissions? In order to understand that, or to assess that, we already know how much energy we are generating by having this system, or we know what is the difference between the energy invested and the energy return. So we have that number, which is our saving of energy, or the surplus of energy. We look to our energy system in the country or in the region that we are here. We are utilizing that technology. Here, these numbers are from the Israeli electric system, but this is already old. This is around 8 years old. So the numbers are different now. The numbers, I mean, the combination of using fuel. 10 years ago, Israel was mainly using coal as their main source of electricity. Nowadays, it's mainly natural gas. So the numbers are different now. But what we do is, like, we look into how much coal we are using, how much gas we are using, how much heavy oil we are using, how much all the different diesel, for example, all the different potential CO2 emission causers in our system. And based on that, we see what is the amount of emissions for coming from that source in our electricity system. So here we see that the intensity of CO2 using coal is around 1 kilogram of CO2 per kilowatt produced. Natural gas has lower number, but it's still a fossil fuel. The heavy oil is even higher, but lower than the coal. So from these numbers, and we know that the electricity production of coal is 75% of the energy mix, then the actual number we have coal contributing to our CO2 emissions in Israel 10 years ago was 0.7 kilograms per kilowatt hour produced. Is this clear, the table? What we did here is, like, we looked into what is the percentage of, what is the percentage of each fossil fuel in our electricity system or energy system. Coal is 75%, gas is 11%, and heavy oil is 14%. This is an example from Israel 10 years ago. And for each one of these fossil fuel types, we know what is the intensity emissions, CO2 emissions per kilowatt hour generated. So by multiplying them, we get to a number that actually says the actual emissions per amount of coal in our system is 0.7 kilogram per kilowatt hour. Why this is important? Because what we are offering here is offsetting a certain amount of energy, of power, by solar energy that we already know what is its energy payback time, what's its energy return factor. We already have these numbers. So here we are saving the system that amount of energy by introducing our solution. That means we are offsetting this amount of CO2 that will not be used anymore by using our system. So in the calculations, in the results that I will show in a little bit, 20-year operation lifetime was assumed for the thin film, because the thin film technology degrades faster than the crystallized silicon. For crystallized, we assumed 30 years operation and degradation of 1% per year of the efficiency of the system. So we got the CO2 emissions, which is the energy, total energy balance, how much energy, net energy we are getting from our system, multiplied by the potential CO2 emissions. And potential CO2 emissions is the equivalent one, which is this number. Equivalent based on, which is the weighted average, actually. Then, and the energy balance is actually the output minus the embodied energy of what we already calculated. And based on that, we can say that actually, if we use single crystalline stationary tilt equals latitude PV power plant, then we know that this is the amount of CO2 that we are offsetting, we are saving our country. If we say, okay, we are using a mix of building integrated photovoltaic, which is multi-crystalline because it's cheaper than single crystalline, and using a rooftop single crystalline and some ribbon or amorphous silicon for the sidewalks, then the amount of energy we are getting from that one, from each one of them, will show us by using this calculation how much energy we are actually saving by, how much CO2 we are saving by using this option. Then, and this is the important one that I'm very interested in, and I think it can be very useful if you are looking into limited land space. Multiplying the CO2 emissions offset that we got by the ground cover ratio gives us the total CO2 offset per unit area, land area. Means if we have 1 square meter of, the area is actually, sorry, one square meter of land can save us this amount of CO2 if we use X type of technologies in this installation type. This is because, you know, this way we account for all the different parameters of the PV system in the study. Everything that we talked about is already, as measures, is embedded in the CO2 emission offset. If we multiply it by the ground cover ratio, which is we just introduced in order to know how much, what is the potential output, we can say that actually this piece of land can guarantee this amount of CO2 emissions. So if you are interested in the outputs, these are what the output calculations of the output of the calculations that we did. So here we see in the location was, as I mentioned, Kibbutz Keturah, and Kibbutz Keturah has one of the highest solar radiations in the region, if not in the world. And we see here that for north-south horizontal tracking, that different type of installation, east-west horizontal tracking, concentration 2-axis tracking, stationary flat plate, that means azimuth is 0 and tilt equals latitude, or polar tracking, or another one which is stationary flat with 0 tilt, like covering 100%. And we see here that the highest is the polar tracking of the potential output, also with the potential input and the potential output. Mainly because polar tracking is utilizing for the two variables, utilizing for our location on Earth, and that's the latitude, and utilizing for the difference between sunrise and sunset azimuth or incident angle. The worst was the stationary, because that doesn't account for any variables. Like the rotation, Earth rotation around the sun has different locations based on the year and the time of the day. So we are not utilizing that at all. here are the numbers founded for the embodied energy after going through the different steps of manufacturing and what's needed to be, what level of manufacturing is needed. These numbers were obtained, were calculated for the different technologies we are considering in this example. As I said, the CDTE and the CIS had the lowest energy intensity or the lowest demand for energy because it's also reflected on their efficiency. You know, I always keep telling people that one of my friends wants to use LED lights for agriculture. And they say that, okay, we can use the light itself as source of energy, so that will reduce our heating load. And I'm telling them, you know, LED has a certain power rating. It's usually like 5 to 10 watts. And based on that, sorry, I live next to the mosque, so we keep hearing that all the time. Anyway, based on that, if your input already is 5 watts, you cannot get more energy out of it. You cannot heat your plant by using an LED light because anyway, the input energy is low. So the output energy, the losses part, the heat losses part of the LED is very small compared to a regular light bulb because of that. And here is the same thing. If you invest less energy in building the system, that for sure means you will get less energy out of it. This is a more detailed graph looking into the energy payback time for all the different technologies. Here we see the single crystalline, multi-crystalline, ribbon, all the different technologies, and on different installation type, north-south, rooftop, north-south open field. And the rooftop and the open field, the main difference is the ground cover ratio here, like how much land we have, how much space we have. Stationary yields equal latitude on the rooftop or on the open field. And you see here the combination of the balance of system and the system itself, the PV module itself. And one of the main results is like on the rooftop, because the support structure already is there, we need less energy for the balance of system. So if we compare the same technology, single crystalline, north-south, north-south, one is rooftop and one is open field, we see for the open field, we have more energy invested in the support structure. And this is one advantage, major advantage of using the building integrated photovoltaic compared to open space, is that we have a significant reduction on the embodied energy used in that system. Here in the flat, in the amorphous silicon, yeah, that's mainly because the energy, it requires more, the amorphous silicon is very thin. It's like a thin film, so you need more support to that than the crystalline silicon, which is more solid. Yeah, here we are comparing these two ones, the CIS and that, and we hear exactly what we discussed. It's like the percentage between the total energy and the breakdown between how much goes for the cell production and how much goes for the balance of system. The CPV or the concentrated photovoltaic, it's a totally different story because the whole technology is different. So we see here that the cell has the lowest, in a way, or the percentage of the cell manufacturing is much smaller than everything else in that technology. And this is why what we said, it's like the cell material is very expensive, it's very rare. So we try to reduce it, but then we invest more in the system itself in order to maximize the energy gain in that system. Again, land use per watt produced, watt hour produced for the different installation types and different technologies. We see as the efficiency goes down, then for sure we need more land. This is like straightforward, but here we show it with numbers. Amorphous silicon always needs more land than the others because in this study it had around 8% efficiency. Then the next one is the ribbon or the CDT and the CIS ribbon as well. And the expectation, the output of this one was that one of the worst technologies to be used is the CIS, because if we, once we look to the different variables, then it shows the worst performance. Energy return factor. And the energy return factor, we said that it is the lifetime of the system divided by the energy payback time. And energy return factor, we see that the two-axis tracking has the highest energy return factor, which means on their lifetime they give the higher energy surplus. Another comparison between the two of them. How much time? Oh, we still have some time. Then we combine that with the CO2 offset per land. So the blue is for the rooftop and the red is for the open field. The main difference between the two of them is the support structure. We already in the rooftop, we're already utilizing a building that's already built. The energy was already invested in building that system, and we are just using that as our support structure. While in the open field, we need to build all that support structure, like the foundations. Now there are different approaches for how to build an open field by ramming instead of having concrete foundations, but still, I don't think that will change the equation that much. And we see here, for example, that if we have limited land, then single crystalline, which has the highest energy efficiency, is much more suitable to be used as flat plate without any tilt than any other technology. And do you know why is that? Even that we said that the tilt equals 0 doesn't account for the changes seasonal and during the day. But here we still had the higher numbers are for the tilt equals 0 for flat plates. Any ideas? Can you hear me? The question is, even that we said stationary flat plate with tilt equals 0 doesn't account for the changes in the amount of solar radiation available. Still, we got the highest CO2 offset per land use. Why is that? What are the factors? How we calculate the CO2 offset per land use? Let's go back. Here. No, this is CO2 emissions. This is, yes, multiplying the CO2 emissions by the ground cover ratio. So we said for flat plate with tilt equals 0, the ground cover ratio is 100%. So we are utilizing the whole piece of land for that. And this is actually showing that the main element in our calculation here is the area, is the land. But then what we need to keep in mind is how feasible is this for us? It's like, okay, we can utilize it. Of course, we cannot get to 100%, that's what we said. In theory, we can assume that, but in real life, we cannot get 100%. We need to have access to do maintenance, service, all these different types of cleaning. And for that, this is not possible. I would say that the current, which is most common right now, is tilt equals stationary with tilt equals latitude, which is this one. We get almost half of that as CO2 offset per land area. There's another reason here as well, other than that 100% ground cover ratio. We don't need that much support structure. The support structure accounts for wind speed. If you have the system elevated from the ground, then that means there is a high potential of wind uplift, that, you know, the wind effect on the system will be higher. If we have it flat with tilt equals 0, then that can be simply on the ground, which means, you know, we don't need to elevate it. There is much less steel used, much less concrete used on that. So that's it. If you have any questions, discussions, then we can have, I think we have something like 10 minutes. Then we take another maybe 10-minute break and come back to discuss the projects. Any questions? I will start calling people by name if you don't ask questions. Katrina, I see you are saying something, but you are on mute. Or maybe you are talking to your colleague.
I was just talking with my colleague, and because my internet connection was unstable and I cannot hear properly, so I was asking.
Okay, I didn't hear the last part, but it's because of the internet connection, so no problem. Anyone? I don't see the full, everyone, so I'll try to. So I will have, like, was it clear? Did you get the main idea of what I'm trying to say? I just need any feedback just to make sure that actually I wasn't talking to myself all the time.
Yes, I think it was clear, and thank you very much.
Good, thank you. Any other feedback? Yeah, we have 10 minutes. I will not stay 10 minutes just asking people if you have feedback. Mm-hmm.
Yes, Natasha.
Natasha, I see.
Yourself.
Natasha, we see that you raised your hand, but we cannot hear you. Am I on the right?
Do you hear me?
Yes.
Natasha from Energy Agency of Republic of Macedonia. I want to ask about bifacial panels. Do you have any experience? Because in Macedonia, the first photovoltaic power plant in the country that simultaneously produced electricity from the sun and the reflection of light was installed in Negotino. The power plant is part of the most modern world technologies made by so-called bifacial panels that accumulate direct sunlight in the upper part, while in the lower part they accumulate the reflection of light from the reflection material, additionally place it under the panels.
Yeah.
And I want to ask you, do you have any experience about these models of photovoltaics? Thank you.
Yeah, thank you, Natasha. It's yeah, you raised a question about the technology that we didn't talk about here, which is mainly in trying to engineer more output per module area.
Мы стараемся придумать новые технологии по модульному типу.
The manufacturing process as an investment. It is actually an investment. We are investing both money and energy in producing a certain technology, and we need our return of investment. We need our energy payback time. We need our energy return factor. So I would say that these two elements should decide what we are going to do. For the bifacial photovoltaic, it's a great idea of actually utilizing more of the, if we look into the equation, what they do in the bifacial is like, here. What they do is like, they cannot control the direct beam component of the collectible energy. So they wanted to increase the diffused and the global radiation by having cells that mainly allocated to collect these two components. So here you are, let's say by tracking or by changing the tilt, you increase the direct beam, or you control the direct beam. And by adding the back side of the panel, you increase the diffused and the global radiation in that. So this way they increase the collectible energy. Now let's look into, so now we know what is the potential increase, what's the potential output of that. Let's compare it to the cost. How much does it cost us? And costing us both in money and energy. It's like, what I know is that they usually use lower grade cells for the backside, not the same, because it's very expensive and they know that the output of these panels is always lower. So let's not invest that much in it. What I would say, in order to evaluate that, I want to see the numbers. I want to see how much energy we invested from that. If we want to talk about engineering, then we talk about energy, how much energy we invested in that, and what is our benefit from having this for the different types of installation. Then we can actually say that this type of technology is more suitable when we use polar tracking or tilt equals latitude. For sure, it's not useful when we use flat plate with tilt equals 0, because there is nothing underneath to reflect. Then based on that number, it's like how much energy gain we have, we compare it to, to the cost of energy. It's like, how much does it save us? How much time does it save us to get back the invested energy in it? This is from engineering point of view. If you talk about economic point of view, then we need to see the cost, how much extra money it's costing us, and in what does it shorten our return of investment period? How many years we will get our money back, our investment back, or not? If it increases it, for sure, this is a losing investment. If it's reducing, then by how much? And we evaluate the initial capital, how much we are investing in the beginning, and how many years we will get that back. So it is a very good exercise actually to be done using this methodology on this type of technologies. We actually, at the Arava Institute, we got a set of bifacial panels just after I finished my study, this one. And I didn't have, I would say, the time and the availability in order to do the same study on these systems, but it will be very interesting to see how they behave. Thank you, Natasha, for being interactive, not like almost everyone else. Other questions? No?
No question.
That's it? Okay, then it's 11:45 here. It should be 11:45 something wherever you are. So let's come back in 10 minutes in order to talk about the group presentations and your final project. See you in you know, let's say at 12 my time. It's 11:74 here already. Yeah, so in 13 minutes. Thank you. Hello again, everyone. Please turn on your camera if you can, so we know that you are back, or just show us any sign of existence.
I'm existing, but without camera.
Okay.
I'm here too, but without camera.
My colleague Aldina is also here, but she doesn't have camera or microphone, just so you know.
Thank you for letting us know. What about the others? Ah, see, Natasha is here. Okay. I see. E.Poroko is here. So we are still missing some. I'm assuming the ones that I didn't hear or see any sign from. Okay. Yeah, so the main focus of this part of the class is, or the session, is to look into your progress in your report, in your project. So actually we are used to do it in person, where the students are, or the participants, you are not actually students, you are participants, are in the same place, in the same location. So
Находятся вместе, в одном помещении. Конечно, тогда легче работать в группах. Но поскольку сейчас это невозможно,
it's a learning process for both of us. So what we think is like this setting will be the most appropriate one to work with. And I think already Abigail sent it to you by email a few days ago. And it has 3 different, or I would say 4 different steps that you need to do. Actually, today we should be at the end of point 3. So you should have identified a renewable energy problem in your country, or interesting for you as a group if you are not from the same country. Present that problem today. You have up to 5 minutes for each group to present their problem. I don't know if we already know who are the groups, if you send that to us already or not, but I didn't see anything about that. I saw, no, actually not anything. I saw few messages in the, just after our last session about people deciding to work together. Then, so we need to know who are the groups, who's in which group, and what is the problem that you are working on. And today also you need to present the methodology, or how you are going to address that problem in your project. And this will be more of a discussion, but it's part of the same presentation. And then you have 12 days until the final presentation, where actually you will present the whole thing, your whole project then. So any points, any discussion, or you want to go directly into the presentations? Is everything clear, first of all?
Yes.
So who wants to start? Let's put it that way.
I can start. from Georgia.
And who are, so you are the Georgian team. It's like a
Yes,
three of
Georgian
you, right?
team, and we can start. I can start if nobody else wants to be first.
Yes, go ahead, please. You can share your screen. I will stop sharing my screen. Just a minute here. Yes, the screen is yours.
Okay. Now I will share my screen. Yes. Can you see the screen?
Not yet.
Not yet.
Ah.
It's coming.
Now it's okay.
Yes.
Yes.
Yes, I will start with a little introduction. My name is Sosomin Diashvili. I'm from Georgia, and I work for the Georgian Energy Development Fund. Also, my colleague who has the first presentation in the first day is Luka Garibashvili, who is my colleague and working in the Georgian Energy Development Fund. And also the third person of our team is Nicholas Sumbadze, Director of Marketing Monitor Department and Georgia National Energy and Water Supply Regulation Commission. Yes, and let's start the presentation. I will share an full screen. Yes, the problem we today want to talk is renewable energy challenges in Georgia, especially it will be about communication problems. On the main problem and obstacle in the implementation of renewable energy projects in the lack of or absence of communication between the population of the region and the company implementing the project. This can lead to protests against the lack of information, and it's often accompanied by manifestations, which is very important factor in this matter. Lack of communication also leads to the project stalling until discussed on the implementation go ahead. And in terms of investments, the problem lies in the lack of investors, which lead to energy shortage and the need to import energy. Yes, and the first slide, I want to say something about the main communication problem. First of all, its initial misinformation. Lack of information on renewable energy projects is a serious problem, not only in the sense to local people. Many protest when the large projects is being implemented in the region, but also the availability of information necessary for fields develop the growth in this area, which is positive impact on region development. And on the conception of establishing communication may be the arrival of interests and the initiations of initiatives by the locals. At this stage, there is a need for the state energy sector to be interested in local initiatives. The second major communication problem is the debate between the renewable energy project development company and the locals. Which is necessary, especially when dealing with large projects. On this slide, you can see the five main problems. This is initial misinformation, opposing from NGOs, which is communicate with the local communities, local opposition, feedback from investors, and at the end, it comes to project files. We have at the first presentation we said about project situation overview. It's like about situation in our country, but it is the local situation overview. It's very important bullets that we want to talk about in the following terms. First of all, it's planned to implement renewable energy project in a specific region. It's a plan to build large generation facility in special region, which generates energy from renewable energy sources. For example, it can be a hydropower plant, big hydropower plant, solar panels, or wind power plants. Part of population opposes such a large project in this region. The main argument is the ecological changes that the implementation of project may cause. It can be flooding of large area in case of water flooding, impact on migration of birds, if the wind power plant is building, and in case of and desertification of the area in case of solar panels, if the solar power plant is building. There's a part of population that understand the necessary of the project and support its implementation, especially the most kind of it. It's the energetics who understand how important the building of large generation object is, and they opposite to the people, and sometimes they can say loud with a loud voice, for how to say it. And the fourth point is the concentrate instinct with the investors. When the investors want to build a large generation object and there is a protest, they see it, and the area where its facilities is to be agreed and purchased by the investors. Construction is suspended to the protest, as a result of which the investors suffer some financial losses, of course. And the 85th slide, I want to say something about steps taken by government. Of course, I will say about steps taken by Georgian government. First of all, the following. Was the government helps to have opening communication channels to the people who protest building big energy generation object. First of all, it was the open channel between government and between the local regional peoples. At the second stage, it was the rise public awareness on the need to implement renewable energy projects. There was a talk about how important this project is and how this can help to the to the country's energy system. At the state level, this can be increased in awareness, but they need build energy and renewable energy facilities. Next, the third step was involve stakeholders in the development and implementation of country energy policy. It was large discussions about between company which is implementation, which is developing projects and want to build a power plant, between the local communities and between government. These third steps was taken, and the fourth step was more complex involvement of different parties in the defining and elaborating for the energy policy in the end projects. And the fifth step of this communication and the steps taken by Georgian government was developing policies and measures to increase community involvement. It's about develop the strategy of energy system developing together with the local communities and companies that are interested in releasing large projects in country. Of course, in our country, in Georgia, it's very important to release big energy, and big power plants. Especially, we can introduce we can say that the hydropower plants is very important and it takes the first step. At the next step, we can release the wind power plants, and at this third step, we can release the solar power plants. But at the first stage, it is the hydropower plants that we have a big potential in it, and we must build we can build hydropower plants with big reservoirs that can regulate the generation of electricity and help countries' energy system to reduce to reduce import of electricity from neighbor countries. This was a first presentation about our project. This was a little overview about the situation and the steps which was taken by the government. And at the end, I want to say something about this picture. This is also a hydropower plant in Georgia. This is a reservoir of hydropower plants. It's located in Georgia. It's called Shauri hydropower plant, and its installed capacity is 39 megawatts. It's very interesting and a very nice place, as you see. And at the end, I want to say thank you for your attention. If you have any questions, I am ready to answer. Thank you.
Thank you.
And I will stop sharing screen. Yes.
Yes, thank you. Thank you. Very interesting. And so if I understood correctly, your main problem is like the local acceptance or community acceptance of renewable energy projects, and that you identify there is a gap there between how the government and investors are communicating that the benefits or what's planned with the community, and you are going to address that, correct?
Yes, it's correct. And at the last years, the last several years, the government started communication and working on it. And we are still developing the strategy of communication between energy sector experts who knows what we need in energy sector and the local peoples who are interested in releasing in project in their region.
Okay, so your main idea, your main solution for the problem is
yes.
Designing that platform for community
yes.
and people to communicate.
Yes, at this time we are working on it, and we have beginning communication between local people and between the governments and between energy sector, and we still starting and that's all. We have not very big experience in it. We just started it, and this is the first step we was taken. The steps that this slide that I showed, the steps taken by government. This was the first experience and first step that we have made.
Okay, thank you, Soso and the Georgian team. I see that Magdalena has a question.
No, I don't have a question. I raised the hand to be the next presenter.
Ah, cool. So Yalla, go ahead.
Okay. I will try, because I'm both on my mobile and on my PC, so I'll try to share the presentation. Is it okay now?
Yes.
Okay. We agreed together with our colleagues from the Ministry and the Energy Agency of North Macedonia to suggest as a project, not a problem, but a project proposal for something that we as a country will be soon obliged to implement in our legislation, as from the obligations that we have towards the energy community and EU legislation that we are transposing into national legislation. So it is titled as Introduction and Development of Energy Communities in the Energy Market of North Macedonia.
Okay.
Okay. We sorry, just check with the presentation. Okay, then. Adică-i dă vacă, așa. Okay. So, as I mentioned, we are obliged to transpose the EU legislation in our national legislation framework. So recently, the energy, we as a member state of the energy community are entitled and obliged to make changes to our laws and bylaws arising from their directives and regulations. A few days ago, the Ministerial Council of the Energy Community has adopted the new clean package, and it was the recast Renewable Energy Directive was adopted as obligatory legislation for us as a member state countries. So this concept called energy communities, introduction of energy communities in the legislation of member states, will need to be adopted in our laws and bylaws. The requirement from the directive says, I will quote, that member states shall ensure that final customers, in particular household customers, are entitled to participate in a renewable energy community while maintaining their rights or obligation as final customers and without being subject to unjustified or discriminatory conditions or producers that would prevent their participation in a renewable energy community, provided that for private undertakings, their participation does not constitute their primary commercial or professional activity. Also, a member state shall carry out an assessment of the existing barriers and potential of the development of renewable communities in their territories. Member states shall provide an enabling framework to promote and facilitate the development of renewable energy communities. And member states, where appropriate, with the participation of local and regional authorities, shall develop suitable information, awareness raising, guidance or training programs to introduce people with this, the citizens with this concept of energy communities. As we first need to define what first the community means and what the energy community means. We have a draft law on communities here, and it says that a community is an association of individuals or legal entities that voluntarily united for their economic, social, cultural, and other needs, jointly owned and democratically governed. As from this, we can have proposal of what the definition of the term energy communities will mean. It can be energy communities are an association of the local population, a group of citizens whose investment in renewable energy sources will result in the development of their community. We've considered a few principles of which the community communication should be set up on. Which is voluntarily and open membership, democratic control by members, economic participation of members, independence, education, training and information, cooperation between communities, and community care. Our proposal is that we can make an assessment of how this concept could work here in our country. Having in mind the requirements of the directive and of course the relevant principles, what we expect to be as an outcome of the project proposals is first of all as required to carry out an assessment of the existing barriers or legal or economic or technical, etc. Afterwards, to enable the needed framework to promote and facilitate the development of renewable energy communities, to analyze the social, environmental, and economic aspects, of course, learn from other countries' best practices if there are any in between our participants, and in the end, to set a justified model on the residential energy communities, meaning that as a pilot project, maybe to introduce this kind of concept probably on a residential building, and how it can work in the future under these circumstances. Thank you.
Okay, thank you. So if I understood correctly, what you are proposing here is how to create, develop, and manage these communities as a proposal for the government, part of the requirement that they have, correct?
Yes, for the government, and to introduce this concept to the citizens.
Cool, interesting.
Yes.
Interesting. Thank you. Okay, I saw a hand raising. Tamara?
Yes, maybe we can go next.
Who are you?
Me and Aldina, team from Bosnia and Herzegovina.
Okay.
I'm going to share my screen now. Do you see everything? Yes?
Yes.
Yes.
Okay. So, like I said, we are a team from Bosnia and Herzegovina, me and Aldina Imširović. One of the main, let's say, problems, issues, or future activities when it comes to renewables is changing our support scheme. Currently, we have feed-in tariffs. They are used as support scheme in combination with annual quotas. As we all know, feed-in tariffs are designed to support the development of renewables by providing guaranteed above market price for producers, and they involve long-term contracts, usually 10, 15, 20 years. Even though they were widely used in Europe maybe a decade ago, they are considered to be effective, but they are not a cost-efficient instrument. And moreover, they are inconsistent with the goal of renewables market integration, which will become relevant for our country in a future market-based electricity sector. In the conditions of an organized wholesale electricity market, large renewable installations should sell their electricity on the market with an incentive added to market revenues. And the main rationale for this policy is the improved operational efficiency of renewables plants and the electricity sector as a whole due to the improved matching of supply and demand. What is important when we are talking about the support schemes is to make a distinction between large-scale and small-scale installations. And EU regulation classifies all installations above 500 kilowatts as a large scale, with lower thresholds allowed in member states' regulation. Since most of our international obligations in the field of energy arise from the Energy Community Treaty.
Обязанности происходят из соглашения об энергетическом сообществе. Это определяет как раз, как организован наш энергетический сектор. И системы поддержки для больших установок должны быть рыночными. И здесь поддержка в основном идет по зеленым премиям или feed-in премиям. То есть это премии, которые платятся сверх доходов от продаж электричества. И это устанавливается административно, и страны ЕС, помимо этого, запускают систему аукционов. В аукционах достаточная степень свободы. Здесь квалификационный отбор на участие идет, и аукционы организуются так, что сравниваются технологии, мощности, география. И большинство государств ЕС используют технологии по региональным или национальным аукционам. И здесь правило ценообразования pay as bid. Плати по предложению. Наша проблема – как перейти от зеленых тарифов к премиям или аукционам. И есть много эмпирических свидетельств из ЕС и Латинской Америки, которые показывают, что аукционы по ВИА, в общем, успешны в снижении расходов на поддержку ВИА-проектов. И мы хотели бы, конечно, услышать опыт других стран и оценить юридические требования по этим проектам и предложить модель, проект модели, как можно реализовать какие новые схемы поддержки в Боснии и Герцеговине. Вот что мы хотим сделать.
Thank you. Very clear. And, Katrina?
Yes, hello everyone. Do you see the presentation?
Yes.
Yes.
Thank you. My name is Stitsenko Ekaterina. I am from Republic of Moldova. Renewable energy in Republic of Moldova. Renewable energy problem in Republic of Moldova. Installation for the production of renewable energy, for example, solar PV installations, wind installations, biogas cogeneration plants, solid biomass cogeneration plants, require large investments and costs. The state does support financing. Thus, all costs are fully on the part of investors. At the same time, the tariff for electric energy obtained from renewable sources is very small. For example, solar PV installation, 1.88 lei per kilowatt hour. Wind installation, 1.45 lei per kilowatt hour. Hydroelectric plants, 0.97 lei per kilowatt hour. Biogas cogeneration plants, 1.84 lei per kilowatt. And for solid biomass cogeneration plant, 1.96 lei per kilowatt hour.
Can you just tell us the exchange rate between the dollar or the euro and the lei?
Excuse me, I don't hear the
exchange rate. How much is that in euros or in dollars? If you can just give us like €1 equals, I don't know how much leis. Okay, go ahead.
Thus, reinvestment does not have time to pay off during the service life of the installation. The service life of a solar panel is from 10 to 25 years, depending on the battery power and production technology, while the investment pays off after 30 years. Only enthusiasts remain in this business. There is another problem. Yes, it would be beneficial for investors if the tariff were as high as possible. But in this case, for the consumer, it's not profitable to pay 1.96 lei per kilowatt hour for energy from renewable sources if he can pay 1.31 lei per kilowatt hour for energy produced at a thermal power plant. The renewable energy sector is not a priority for the state. There is a lot of bureaucracy. Such moments as the collection of all necessary documents, papers, signatures, and the conclusion of contracts with various institutions, and lack of reliable and detailed information. As a rule, the investor himself learns about the possibility of producing energy from renewable sources, himself finds information and answer to his questions. This is a very long and completed process, so many give up their idea halfway through. Thank you.
Okay. Thank you. Can you just like say in one sentence, what is the problem that you are looking into? So I saw that, okay, if I understood correctly, the feed-in tariff is very low. It ranges between 5 euro cents to 0.5 euro cents to like 1 euro cent, in that range. And what you are proposing is to, I lost you there. So the current problem is the very low tariff, and what you want to do.
Для начала, получается, нужно увеличить этот
So
тариф.
to begin with, we need to increase this tariff.
Но это будет выгодно только для
But that would be beneficial to investors only.
Тогда для обычных
And then
потребителей
to ordinary consumers,
все равно откуда получать. Зачем нам
it doesn't
переплачивать?
make sense where they get the electricity from. Why should they overpay?
Просто если действительно мы хотим поднять этот
If we
вопрос
want to
возобновляемых
raise
источников, да,
this
в
matter
первую
of
очередь,
renewables, first and
в первую
foremost,
очередь государство должно
the
помогать
government
финансировать
has
инвесторов,
to
которые
help
заинтересованы,
financing
чтобы продвигать
the investors who are
возобновляемые
interested in that, in promoting renewables.
То есть на законодательном уровне.
And it should be done at the legislative level.
Okay. I see 2 hands raised. So?
Да, я хочу спросить, у вас есть какая-то
I
статистика?
wanted to ask you a question. Do you have any statistics, any action plan that would help you solve this problem? Do you have a strategy with the help of which your government would be able to attain the goals? Sorry, so was it a question addressed to me? Yes, sure. So you're asking whether the government has a scheme to solve this problem? Yes, exactly. Is there any, first of all, statistics, and is there a strategy, some action plan, some scenario, or anything of that kind? We have a scheme of governmental support, actually 3 schemes: net metering, fixed tariff, and fixed price. But again, if, for example, I want to install a solar panel, it all lays as a burden on myself. So I need to transport, buy, install the panel. It will all be at my cost as investor. That is why a lot of people at first are willing to do that, but then they abandon this idea because it is a really highly expensive installation and it will not pay back. That's why a lot of investors would like to get assistance and support from the government. They want financial support from the government to the people who would like to promote renewable energy. Thank you.
Other questions, or it's Jordana? Is that the right
Thank you. I would like to show presentation about Serbia because
yeah, before we start with that, I want to ask Vladislav if he has a question to Katrina, or
no, we are in the very similar situation.
Okay.
Yes,
okay.
yes.
Okay. Go ahead. Sorry.
Is it okay? Can you see? we are at a very similar situation like Bosnia and North Macedonia and Moldavia. In our energy development strategy until 2025, we estimated our RES potential. Total available potential in Republic of Serbia is 5.65 million tons of oil equivalents, and we don't use our potential. We are using only 2 million tons of oil equivalent renewable energy sources. On this slide, we can see total number and capacity of RES power plants in Republic of Serbia at the moment. We have 450 RES power plants with total installed capacity around 3.2 gigawatts. Regarding built RES power plants, we have 333 power plants with total installed capacity around 3 gigawatts. On this slide, we can see impact of feed-in tariffs in Republic of Serbia. We started in since 2009 until now, and what happened in Serbia. We planned in our national energy plan for renewable energy sources to build around 1,000 megawatts of new power plants in feed-in tariff systems. But until now, we managed to realize around 800 megawatts, of which 500 was built and 300 is under construction. It is not sufficient. It is not in line with our plans. In feed-in tariff system, we now have 277 plants with installed capacity around 500 megawatts. Regarding RES share in Serbia, we didn't achieve our goal. Our goal for 2020, set goal for 2020 was 27%. We achieved in 2019 to 21.44%. Our plan was 25.6. We are almost 4% under our goal for 2090. And what we done after these results, we adopted our first law on the use of renewable energy sources in April this year. Main goals are to preserve the environment and to make the growth of RES more dynamic. Key novelties in our new law: market premiums are introduced as in other countries. Feed-in tariffs remain only for small plants and demonstration projects. We introduce corporate PPA, and we introduce prosumers and net metering. Citizens also can form a renewable energy community. Our law recognizes green hydrogen as an energy source. It can be used in traffic, heating, and I can't, okay. And we introduced the digitalization of administrative procedures. We introduced e-energy with our law. And very important, we introduced public tender for the selection of a strategic partner, which enables Serbia to attract new and additional investments in the field of renewable energy sources. We also, with new law, guarantees the security and predictability of support schemes. Support schemes may not be subsequently amended by regulations in a way that reduces and limits the acquired rights from support schemes. The main point is support schemes for the production of electricity from renewable sources are applied through two systems: the market premium and feed-in tariffs. Plant that can get incentives are wind, solar, hydro, biomass, biogas, geothermal, and biodegradable waste. Support schemes are given for electricity produced in newly built or reconstructed power plants that use RES. A market premium system is introduced for the first time. The market premium is determined in euro cents per kilowatt-hour in the auction procedures. Support period is 15 years, and they gain priority access to the systems. The government sets quotas in megawatt of installed power plant, and the energy agency determines the initial price for the auctions. The Ministry of Mining and Energy initiates the auction procedures by public invitations, form a commission for conducting the auction, makes a decision on the best bid. After auctions, the power plant gained the status of temporary privileged producer. The status lasts for 6 years and can be extended for 1 year. Feed-in tariff systems remains also for small plants below 500 kilowatts or 3 megawatts for wind power plants and demonstration projects. They have exemptions from balance liability and balancing cost, incentive periods of 15 years, and they have priority access to the system. Auctions will be in 3 phases: qualifications, bidding, and best bidding selections. Our transmission system operator is obliged to keep an electronic centralized and publicly available register of all connected power plants that use renewable energy sources, and all documents must have the form on electronic documents. We adopted almost all bylaws by the law on the use of renewable energy sources. Energy agency adopted methodology for setting market premium, for setting feed-in tariff, and they adopted decision on setting maximum repurchase price for auctions for electricity in wind power plants. It is 5.57 euro cents in kilowatt-hour for wind power plants with capacity higher than 3 megawatt. And I think the main problem is it is almost 50% of feed-in tariff. We are not sure that first auctions will be attractive for new power plants. This is basic auctions details. We set quotas 400 megawatts for first wind auctions and the financial instruments for application for auctions and sorry, and we provided software for auctions, and also we introduced e-energy, or because to simplify administrative procedures and to fast it. And we are in front of our first auctions. We don't have any experience, and we would like to share experience with other countries in the same situations. Thank you.
Thank you. So I got a message from Tuta. Is that the right way of pronouncing the name? From Albania.
Yes, sorry.
I cannot hear you.
Teuta Timio from Albania. Yes, I have a presentation, but can I?
I don't know if it's something wrong with your connection, but the voice quality is very bad.
I don't know. Sorry.
speculative. So just for the sake of time, is there anyone else who is presenting today that they don't have, they didn't? So we have already 5 groups, and Tuta, is that the right name to pronounce, the right way to pronounce your name? Hello?
Sorry.
No? Yeah.
I hear you very very good. But
So,
do you hear me?
You have very not good connection.
Yeah.
Sorry. We don't understand you.
I'm sorry. I'm sorry for that.
I think if you lower the volume of your speakers, maybe it will be better.
I don't know.
No, it's not only. So you have a presentation. Sorry, but you have the presentation about the project, or it's something else?
For Albania,
But your group project.
Yes.
Yes. Okay. So let's try to go over that. And see how it goes in the first time. But if we manage with it now, then we'll
share
screen.
Yeah.
Yeah. Okay.
Okay.
It's okay?
Yes, we see your screen.
Yeah, okay. Okay, I'm Teutafimia from Albania. I work in Renewable Energy Directory, National Agency of Natural Resources. I have Master of Civil Engineer, and I am Head of Waste Monitoring Sector in this agency. This is a map for Albania. Some information. We have 2.8 million people. Capital is Tirana. We have 90% of electricity produced by hydro, and GDP in 2016 is 10.5 billion euro. For renewable energy in Albania, I say that Albania has prepared 3 important documents: Action Plan for Energy Efficiency, that is approved, Action Plan of Renewable Energy, and the National Strategy of Energy 2030. The share of RES in overall energy in Albania determined by hydropower and firewood. The Albanian government has been focused on the diversification of its supply with energy and the promotion of other renewable energy sources, such as solar energy and wind energy. We will expect that the share of energy from renewable sources will grow towards the target set for 38% in 2021 and 42% in 2030. You can hear me? I'm okay.
Yes, you're okay.
Yes, you are okay, but you just said in the first slide that you have around 98% hydro, right?
Yes, it's true.
So you don't count that as renewable energy in your energy mix?
We have 90%, 90% hydro, but we didn't fulfill our requirement for energy. So we, because we depend from the climate. For this, our government works to diversify these sources, because for this reason.
Okay.
For legal framework for this, we work a lot of to approve the many laws and sub-laws. Our laws for this are two on the promotion of renewable energy sources, 2016, and on sector of electric energy, and some decision of Council of Ministers for action plan of national renewable energy, for approving the rules and procedures for the construction of new capacities of electricity generation that aren't subject of concession, on approving the methodology for determining the purchase price of electricity produced from small renewable sources of sun and wind, and adopted of support measures to promote the use of electricity from renewable sources of sun and wind. As I said before, Albania has considerable hydropower potential, where only 35% of it is used. We have a lot of hydropower plants. The support is granted through the feed-in tariff after a concessionary agreement has been reached. The PPA for this plant change every year and is based on the Hungarian Payback market price plus 15% premium for 15 years. Also gets energy purchase first, very high dependency of climate. For example, 2016, one of the best years for hydro production. We were net explorer. 2016, one of the worst years, and hydro capacity only covers the losses in transmission. Wind potential. Generally, we have a low wind speed. Permits for wind farms we have been given, but not development. The first auction scheme for wind power will be developed soon. Solar power potential has been assessed in 1,500 to 1,1600 kilowatt-hour per square meters per year. We have a lot of power for solar, and we have 240 days to 300 day in a year with solar. We are supported schemes for solar and wind through three schemes. Installation up to 2 megawatt of solar and 3 megawatt of wind getting feed-in tariff. The price of support has been established by the ministry and approved by the regulatory entity of energy. The price for 2017 is €100 per megawatt hour for solar and 76 euro per megawatt hour for wind. This price is subject to change every year, based on technology and economic factors. Is very high interest from developers. The first
Девелопер является собственником земли и
produce the electricity. They are under certification phase. They are 12 plants, 2 megawatts that are under certification phase. My sector is working for this certification. Support scheme for solar and wind through auction. For the first time, the government has developed the auction scheme for solar capacity of 15 megawatts of installed power. The government offers the land, the connected point to the grid, the PPA for 15 years. The developers with the best project and lowest asking price for megawatt hour is awarded as a winner. After the creation of the liberalized market, the support will be through the contract for difference. Other schemes is the net metering. The scheme will have the following basic principles. Yearly netting, zero surplus energy at the end of the year. The ministerial and regulatory entity will approve the price of purchase for the electricity injected to the grid. At the start, it will probably be the same as the retail price in order to have a fast uptake and development. The maximum allowed installed capacity is 500 kilowatts. Okay, this is a table that presents the capacity of solar and wind in Albania. As you can see, the photovoltaic project up to 2 megawatts in production are 12 and for the wind that equipped with final approved are 5. Okay, so this is my experience. I work mainly for energy efficiency buildings, and for last 5 years I work for renewable energy sector. And my work in this sector is to participate in the working group for monitoring and certification of solar and wind plants in Albania, up to megawatt and wind up to 3 megawatt. So this is my presentation.
Okay, thank you very much.
You are welcome.
So this was supposed to be in the first session, right? Your presentation about your country's presentation. Is that correct?
Yeah.
Yeah. Okay. Thank you. So what one of the main objectives of today's session is to see where you are with your project. I will put the slide again for like a few minutes. We actually are way behind time. But what we need you to do is, this is just a reminder. First of all, you need to identify a renewable energy problem you have in your work group or in your country, depends on how your group is formed. I think for now we're having country-based groups. Then today you are supposed to present that problem and your suggested methodology of how you are going to address that problem. And the final product, which will be in December 12th, is actually presenting the whole thing. You are presenting, 2 slides background about your country, 1 slide identifying the problem, 2 or 3 slides how you are going to work with it, and a final slide of the final product or the final project. So what I noticed today is like there is very few who already have a clear definition of what the problem is. I mean, by clear definition, that's we as observers understood what you are trying to identify as a problem. Maybe most of the time that's the case, that you already know, but because you speak the language of your internal organization, your internal, you are part of that structure. So you identify the problem, or you describe the problem according to how you understand it, which is one of the main problems in presenting your work to the public, to people outside your organization. So what I notice is like there is no clear definition of the problem. And also there is most of the presentations, they didn't actually talk about how you are going to address the problem. And it's actually related. If there is no clear definition of the problem, then for sure there will be no clear steps of how to address that problem. So my suggestion is actually, first of all, work together as a group. And I saw that most of you are already doing this, which is great. Try to have 1 sentence for the problem. Describe the problem as 1 statement. Having 1 slide for the problem itself, which helps you in understanding what is your scope of this project, and then address that problem by showing, 2 or 3 steps that you need to follow in order to solve that problem. And then based on these 2 or 3 steps, you'll develop your methodology. If it's needed, I will discuss that with Abigail, and also she will discuss that with you. If needed, then we'll add another session before the 12th, or no, I see it's the 14th actually, it's 12 days, the 14th of December. Before that, in order to help you or to go over of what material you have ready, the presentation, in order to make sure that actually things are according to what are the expectation or the goal of this course be. Is there any questions, any feedback? I see that Soso has a hand raised.
Yes, I want to say if something interesting in presentation in terms that we tell today, we can make our group larger and add someone from different countries. If someone is interesting in it, of course, we can work on this problem together. I think it will be interesting.
Yeah, good idea. And also you have the WhatsApp group. You can discuss, have different dynamics over there of like discussions and people joining other groups and all that. And maybe you can have a subgroup on like a WhatsApp group for your work group together.
Yes, yes. Who is interesting, we can make a small group on our project together and work there.
Yeah. So my main feedback about today is that you have to maybe use one slide, one sentence in that slide to describe the problem. What you need. This way will make you more focused and actually, focus is the right word. It's like to have an easier outcome by looking into that statement. Every time you think of the methodology or the solution, you go back to your problem statement and just make sure that you are addressing it. And more clear steps in the methodology or the solution that you are proposing in order to get more of an action items. It's like what needs to be done in order to address that problem. Okay. Any other questions, feedback, discussion? Anyone wants to complain about the weather? Okay. So you want to say something?
I think everything is clear and we can start working.
Thank you. Okay, thank you very much, everyone. Ora, do you have any announcements or we can finish?
No, thank you very much to everybody.
Thank you all.
Thank you very much.
Have a great day. Bye-bye.
Good luck.
Good luck.